Okay, carrying on here with Lewis structures, and I grabbed a clean piece of paper. We kind of had gone around the edges there of some of the next couple examples, so we'll start over with a fresh paper here, and we won't see as many issues, I think, for the rest of this page at least, so maybe we can keep from making too much of a mess of it. The next molecule here is carbon monoxide. So to draw the skeleton, we would connect the carbon and the oxygen. Diatomic molecule, that's pretty straightforward. Carbon brings 4 valence electrons, oxygen brings 6, that's a total of 10. Right? One bond there, we already used 2, there's 8 left. Right? That actually might ring a bell with you. Adding 8 electrons here, let's do it like so. Right? That would give us one atom with 6. The other atom also has 6. If I do it 4 and 4 here with the electrons. So to satisfy the octet rule, I need to share a pair from each of the atoms. And I end up with a triple bond and then one non-bonding pair on each atom. That's exactly what we saw for N2. It's also a diatomic molecule that had 10 electrons. And that's the kind of pattern I'm kind of hoping you'll be thinking about and looking for in your structures, because we really don't have that many options in terms of valence electrons and which atoms have which sets of valence electrons. So we will see structures repeating over and over again when they fall into the same categories. And if you've got your eye out for that, this will start to become sort of a second nature thing. You'll just have a grasp of what the structure is going to have to look like because it'll relate to things you've already seen. Now, in this case, right, the reason why this one comes after CO2 is because there's formal charges here, right? And it's an excellent point to recognize. You need to satisfy the octet rule first before you worry about formal charges. If you get too worried about formal charges, you can end up in a bad structure because you worry about formal charges first before you've satisfied the octet rule. If we satisfy the octet rule here, we get this structure. This structure has a negative formal charge on this side, right? That carbon, the formal charge would be 4 minus the 3 bonds minus 2 non-bonding electrons equals -1. So it's negative on the carbon side. It is positive on the oxygen side. 6 minus 3 minus 2 is +1. This has a positive charge on the oxygen side. Now, that is still the correct structure. There's no way to get rid of the charges here without violating the octet rule. If we tried to share this pair of electrons on the carbon and make 4 bonds between the oxygen, that would take the oxygen to 10 electrons. Oxygen cannot do that. It is not big enough to hold 10 electrons. So this is the best structure that we can get. Now, this is also a good indication of how carbon monoxide reacts. You may know carbon monoxide is a poisonous gas. You breathe it in. It actually bonds to the iron atoms in the hemoglobin in your bloodstream, and that prevents you from carrying oxygen to your tissues and to your brain. And the reason it does that is because this carbon is reactive. This extra pair of electrons on this carbon is really likely to try to make a bond with that pair of electrons. If it makes a bond with that pair of electrons, it loses the negative formal charge. It becomes more stable. When carbon kind of sees an empty orbital on the iron in the hemoglobin in your red blood cells, boom, makes a bond to it. Sticks there, and it sticks there much stronger than oxygen does. So where oxygen bonds to hemoglobin in your lungs when you breathe it in, it then leaves when it gets to the tissues that can then use it, like working muscles or your brain. Carbon monoxide doesn't do that. You breathe in enough and you limit your body's ability to take oxygen to your brain. That could be fatal. Okay, but the other option here, right, if you get too focused on formal charge, what can happen here when you draw carbon monoxide is maybe you stop at a double bond. So if you just make a double bond coming from, let's see, would you just make a double bond? Yeah, if you just make a double bond coming from the carbon side, and you just leave 2 non-bonding electrons on the carbon, but then still have 4 on the oxygen. So that would be just this first arrow coming in here. If you just do that, you actually do end up with zero formal charges. This carbon, 4 minus 2 minus 2 would have a zero formal charge, and this oxygen, 6 minus 2 minus 4 would have a zero formal charge. But this does not match the known and observable reactivity of carbon monoxide. This carbon, having only 6 electrons, would react in a way that it would try to get more electrons. That is not what we see in the way carbon monoxide reacts. It reacts in a way to get rid of electrons. So this is the proper structure, matches what we can observe about reactivity. This one is not. This is the opposite of what we observe. And that's why it's important to do the octet rule first, then worry about formal charges, and not the other way around. If you let the formal charges decide the structure, but you ignore the octet rule, you can end up with an incorrect structure that really doesn't give us an idea of the bonding, which is, again, what we're trying to do here in this situation. Okay. Now, Cn minus, right, this is something that may look kind of familiar here as well, but we do need to think about how do charges play a role here in our structures. Just 2 atoms, we would draw a skeleton like so. Right? But now, when we're counting electrons is where we first need to account for this negative charge. Carbon brings 4 valence electrons, nitrogen brings 5, but because there's a non-zero charge here, we've got to account for how does the charge relate to how many electrons are present. If there's a negative charge, that means there's 1 more electron here than we think. So we're adding 1 more electron to account for that negative charge. This is also a 10 electron diatomic molecule. Just like N2, just like CO, right? We're going to go through the same set of steps, but we'll arrive at a similar structure. Okay. Now, because this is an ion, right? So how you count the electrons, you have to factor that in for ions. Because this is an ion, we'd expect to see a formal charge in this molecule. There should be a negative formal charge, right? But there doesn't have to be a positive. We could have a neutral atom and a negative that would match here, but the formal charges will add up to the total charge. They add up to 0 back here for carbon monoxide, right? A +1 and a -1. There should just be a -1 here. And since we can see the carbon is in the same environment as the carbon in carbon monoxide, that's where the formal charge is. Right? 4 minus 3 minus 2. Negative on the carbon. The nitrogen is neutral though. 5 minus 3 minus 2, that is a 0 formal charge. So the only negative charge there is on the carbon atom in that molecule. Okay. Now, moving on. Water, H2O. The first thing we would do here is draw the skeleton of H2O. And the last thing we said from our handout was that we want to put the least electronegative element in the middle. But there are some exceptions to that. Because if we look at these, hydrogen is actually less electronegative than oxygen. Now, it's a little hard with periodic properties, since hydrogen is way over here, but if you do just look at the values, oxygen's 3.5, hydrogen's 2.1. Oxygen's more electronegative. Just based on that, we'd imagine hydrogen should go in the middle of this molecule. But if you look back at point number 1, right under the top of writing Lewis structures, right, there's a little sentence at the end that says, hydrogen and fluorine are always placed on terminal positions. Now, the reason we do that for hydrogen is because it can only make 1 bond, right? You don't want to be in the center of a molecule if you're limited to making 1 bond, because then you couldn't have a second atom attached. So hydrogen always goes on the outside. Fluorine, it's more electronegativity related. We can't make a second bond to fluorine. That would cause it to end up with a positive formal charge, or with more electrons than it could hold. So fluorine's always going to go on the outside as well. That means our skeleton here should be oxygen in the middle. Right? Not because it's less electronegative, but because it's the only atom that can make more than 1 bond. So that's the case. We'd have that skeleton. 1 electron from each hydrogen is 2, plus another 6 from the oxygen is 8 total electrons. We used 4 here already. We made 2 single bonds. That means we have 4 left. Now, hydrogen already has exactly as many electrons as it needs. It's got 1 bond, that gives it 2 electrons, that satisfies its duet. All 4 of the remaining electrons can go on the oxygen, right? And here's a case we said before, be careful about putting electrons on the central atom. Right? In this case, we have nowhere else to put them. So they do go on the central atom, and in fact, the oxygen needs them to satisfy its octet, right? And we would actually have zero formal charges everywhere. So that would be a good representation of our water structure. Right? We see something very similar with ammonia here, NH3. Right? Hydrogen can't go in the middle, so the nitrogen does. We attach all 3 hydrogens to it. Right? We count the electrons, 5 from nitrogen, 1 from each hydrogen is 8. We already used 6. There's 2 left. The only place we can put them is on the nitrogen, right? And we end up with that structure for ammonia. That also has zero formal charge everywhere, right? And octet and duets are all satisfied, right? And moving, right? Trends in the periodic table here, moving to carbon, right? Hydrogen can't go in the middle, so carbon has to go in the middle. We connect all of the hydrogens to the carbon, right? And we've used up all of the available electrons. 4 plus another 4 would be a total of 8. We made 4 bonds connecting those hydrogens. And that got us to a structure that has a duet for every hydrogen, an octet for the carbon, and everybody has a zero formal charge. So that would be a good structure as well. Now, with carbons and hydrogens, we'll see things can get a little more complicated, and we'll start to talk about those in the next video.